Today I'm here to tell you about a resource that I suspect not all of you are aware of, and I'm going to try my best to advertise via our example. So, as you might know, okay. Can I just have a quick poll of who has seen this graph before as a warm-up? Okay, that's pretty good, even Florian, I think, remembers. So it turns out that mathematicians often construct and craft examples and counterexamples, and then they use those to get an intuition on their hypotheses, among other things. Or maybe they use the examples and counterexamples to demonstrate when two things are different. So the weaker, there's an example that might have one property but does not have a stronger property. So that might be a useful thing to have and maybe sometimes even formalize. And, okay, let's just see. Oops. Oh, I see the double jump again. Can I get to the next slide? No? Can I get it here? It has possibly disappeared. Okay. So this graph is, for example, a good example of such an example. It's the only one of only 13 cubic distance regular graphs. And it has another property and non-property. So it has a Hamiltonian path. And as you can see, it's easy to find it. That's a path that visits all vertices exactly once, but it does not have a Hamiltonian cycle, which is slightly harder to prove. And this is a small foreshadowing of things to come. But that's hard to prove. How would you go about formally proving that this graph is connected? I'm gonna give you a second to think. Okay, getting some laughs there, that's good. So it turns out that graph theorists come up with more examples, and they sometimes collect them in databases. So that's our favorite one today, the House of Graphs. And mathematicians even collect examples into databases very broadly. So here are some of the more famous examples up there for you. You might recognize some of them, you might not. I'm going to mention some of them as examples of things as I go further. But one way to think about them is that, you should know that how the databases are structured really depends on the area and the objects that they talk about. And in general, people use them as reference and a way to test hypotheses or look for counterexamples. And as a small advertisement, there are many, many more. And you can go to mathbases.org, which is a pet project I started, and it has now grown, to look for more. And just to convince you that there are many of them, here's the first page of the listing from mathbases.org, second page, third page, and fourth page. And I'm sure we're missing many, many more. So there are lots of things out there that you can formalize if you want, or you can gather examples from if you want. Okay, so how do they look like? For today, this is a good mental model you can take. So you have a list of objects, and then some databases might even contain a list of properties, and then the values are whether an object has a property or whether a value for such and such property for that object. And broadly speaking, there are two types of values you can have. The one we're more interested in today are results of computation, so whether a graph is bipartite, whether it has a Hamiltonian path, and so on. But there's a lot of databases have more curated entries, so where in some places you might have the fact that this object has such and such property is evidenced by this theorem. And they might have a reference there. Okay? And this will, if you want to formalize or incorporate such a database into a proof assistant, the shape of the database is going to force your hand when you pick a strategy. So one obvious thing is how many objects are in there and how complicated they are. And the other thing is how many cases or how many properties you're trying to deal with and how difficult those are. And I think I can segue smoothly into describing the house. Yes?
I've got a question. I remember when I was a student in the library, there was a giant book called the Atlas of Finite Groups.
Yes.
Has it been turned into such a database?
So the best group resource is the library of small groups that you can access from GAP and Sage. So small groups library. And I think they have all groups up to, I think, 1023, and then they give up on 1024, if I remember right, and then keep going for a while, but it's not exhaustive anymore.
So this wouldn't have the monster in?
I'm not sure whether it has the monster in there. I don't remember. It would involve representing all the generators at the very least, and I'm not sure.
Find a simple group that
But
has the monster away.
That's the character.
I don't know, but at least I have this picture of the pages. I had no idea at that time what it represented, but it seems hard to fit in a little cell of a table like this. It really had a lot of information, character tables.
Yes. Yeah. So I think the small groups library doesn't have all of those, and I can go on, and there probably James can tell you maybe more about the small groups, right? Did you ever use it? I never ended up using it.
Yes, I mean it is what it says. So the monster is not a small group. In the sense of the small group library.
Yeah.
I mean the monster is in GAP, but as a one-off object, not as part of the library. Is the point.
Yeah. Okay.
There are other groups like that. So we have the database of all groups in GAP is a small group library plus a bunch of solitary ones, as it were, just like classification itself.
Sporadic ones.
Okay. I guess no spoilers at this point. We tried to incorporate the House of Graphs, which is a database of interesting graphs, where a graph is interesting if graph theorists think it's interesting. The main reason, I guess, why we chose the House of Graphs is because my background is in graph theory and groups, and I understood this database. That's how it came about. But it's interesting because it has loads of graphs in it, and it also has a large number of properties, and the combination of the sizes of graphs and the computational complexity for some of those graph theoretic invariants don't mash up so well. So they compute the values for them, and you have lots of entries that say computation timeout in the database. So I think they have a 5-minute limit, which is reasonable when you have 32,000 graphs. But just to say, it's not something where you want to hack together an algorithm in Lean that will compute things for you. So I'm not sure it's quite up to standard of specialized solvers for those properties. And just to give you an idea, here's a picture. Turns out I was wrong when I estimated the average order of the graph. It's more close to 52, and that's mainly because there are a ton of graphs on 30 vertices in it. All right. So let's step back. If you want to import or incorporate a database of some sort of mathematical objects into a proof assistant, you have some design options for your library. The first one, if you have 5 examples and you just need to prove 1 or 2 properties, you might go the crafted by hand way. And if you're just interested in proving that the Peterson graph is connected, then that might be the way to go. If you if you've decided to do the house of graphs, then there are absolutely too many graphs in it to do anything by hand. And too many properties, and some of them are too difficult to compute to go essentially develop a computer algebra system in Lean. That's a different project, probably very worthwhile, but I think too difficult for me to attempt on a first attempt. And then you have sort of two reasonable things that you might try, or two things that we thought would be reasonable, to use a combination of encoding some properties for a SAT solver, verifying the encoding, and then using that combination to convince Lean that something is true. Or you've heard a bit about certificates today already in the previous talks, and I'm going to say a bit more later. But you could use some kind of external software to compute the property for you, compute also a certificate that gives you additional data that convinces Lean that something holds. Okay, so obviously we went this way. Just a word about certificates in case people are in the audience that aren't so familiar with them. So the idea is to give yourself additional information that makes it easier to check. So a simple one is, it's easier to check that the product in the second line there is equal to that number on the right than it is to just checking that the number is not prime. And I trust that everybody's already verified for themselves that those two things on the left are primes. Another thing you might do.
You don't need that.
You don't need that.
You don't need them?
You don't need the true factor to be prime.
Oh, yeah, no, but I gave two big numbers. I tried to make it difficult looking. So, similarly, when you're dealing with graphs, it's a lot easier to just check that the path satisfies the property of being Hamiltonian than it is to find a path, or to find the cycle. Okay. So the nice thing about certificates is that they give you a reason for why something holds. There's they are explaining the proof to you. Like, here's a Hamiltonian path. That's why it's true. We can construct it. Unfortunately, some properties don't have good certificates. And this is a standard technique in computer science, and I think even in combination with Lean, if I remember right, it was used to get some information from computer algebra systems. Mm-hmm. Yeah, okay, see Rob nodding there. All right. But I don't think anyone has used it quite at this scale yet. Okay, so we started, for now, relatively small library that allows you to import graphs from the house of graphs into efficient representations that you can compute with or check certificates on in Lean. Together with those certificates, so we get the certificates from the outside. The outside might be a SAT solver. And then Jure has also prepared two nice tactics. One that allows you to search the database around Lean and get examples in the info view, or to close a goal by when a goal can be closed by finding an example. An interesting bit here, we didn't do a lot of benchmarking, but we can tell you that just checking the number of components takes some time. So the database says that that graph has that number of components, that graph has that number of components. Checking that on all of them takes that, and that even means that we needed to exclude about 5 because they time out.
So this is just a one-time cost, right?
Yes.
You can ship it and say, here's all the proof.
Yeah. No, I think if you want to actually load that into Lean, like to have it build the proofs, that takes 60 now.
Yeah.
I mean, you can save the build.
Yeah, you can save the build, yes. Yeah.
All the Olean and then it.
Yeah, you can save those.
You should be able to
produce the proof fast? I mean, if you put in the proof, then it doesn't have to find the proof, right?
That's partly why I put that here, to get,
But this is verifying the certificates.
yes.
When it says it's connected, it's probably easy, but when it says there are 3 connected components,
No,
I mean, there are certificates for connected components.
the connected components, Jure will go into detail about explaining that certificate, so I'm going to leave those questions for Jure. I think I have a few more things to say. So, when you try to get graphs into Lean, it turns out that's not a great way to do things. So if you have the adjacency relation, it's not going to be easy even to just check that, say, if you have a coloring of vertices, that it's a valid coloring that does not allow adjacent vertices to be of the same color. It's better to have a set of edges, and then it's just going to be linear in the set of, in the size of the edge set. Or a super simple property, whether a graph is regular, so all vertices have the same number of neighbors, is trivial when you're given a neighborhood map. So for each vertex, you get a list of its neighbors, compared to just having the adjacency relation, or even just the edge set. Which means that if you want, because though you want to do those things all the time, when you have 50 properties, you actually need different representations of graphs, and you need to prove that they're equivalent. So there's no way you can get around it. Or at least we don't think there is.
How do you know that the neighborhood sets are correct?
Yeah. You have a proof, and you say, yeah, you check all that it aligns properly.
I guess there are many more properties than representations, so it's still worthwhile.
Yes, yeah, you have so many properties that it's worth investing in the equivalence. It pays off later on. Okay. So I already mentioned some of this. So it turns out that all of those properties, or checking the certificates, there are 2 main things that you want to do non-stop. The first one is checking that something is a member of some set, where those 2 sets are going to be either edges or vertices, or something, or maybe something in the neighborhood map. But you need really efficient membership checking. And you also want to check something for all elements of a set. So all edges, all vertices, all neighbors of a vertex, things like that. Which means that we ended up using a very computer science implementation of sets. We went with red-black trees just because that's in Lean. We decided to not go more efficient yet. That's good enough for now. And also, and already said that we have 2 representations that we currently know are equivalent. And we might need a further one, so we might need adjacency matrices at some point.
Okay, right. So I'm gonna show you how we did 2 of the invariants. The first one is connected components that Katja has already mentioned, and first I'll show you the definition of the connected components. So first we define the connectedness relation on a graph, which is the pretty intuitive one, or one you could expect, is that it's just the equivalence relation generated by the adjacency relation on the graph. And with this we define, with this we define the structure that explains the connected components of a graph. So the connected components of a graph have the number of connected components, a function which for each vertex assigns which component it's in, and then 2 properties which need to be satisfied. So each component needs to have at least 1 vertex in it, and we want to say that this component function, which assigns components to vertices, coincides with the connectedness relation on the graph. So this is our definition of the connected components of a graph. But yeah, now the question is, if we have a concrete graph like the Peterson graph, how do we show that it's connected? And for this problem, there's multiple possible answers. One would be to implement an algorithm which computes the connected components and prove it correct in Lean, but as we've seen, that can be a difficult, so what we did is we externally computed some certificate and then imported it into Lean and then showed that that gives us the connected component. So the certificate for connectedness that we used is a rooted tree in the rooted spanning tree in the graph. So we can take the graph outside of Lean and we can compute this rooted spanning tree, which basically says that we have some root of the tree and there's a kind of a next relation which takes a vertex to closer to the root. And then we encode this certificate into Lean in the following structure. Oh yeah, and the question is, what if we have multiple components of a graph? We just compute a spanning tree for each of the components. So really, for the whole graph, we compute a spanning forest, and each of the trees gives us one of the components of the graph. So in Lean, we define this certificate, which basically we can split up into a bunch of data that we can compute and a bunch of properties that we need to check. And data is basically, again, the number of connected components, the function which assigns the component to each vertex, and then some things which says that this is a rooted spanning tree. And if you look at each of these properties for a while, you can see that they're all kind of efficiently computable. They're all linear, so they're easy to check in Lean. Yes, there's a question.
So you also need something that tells you for each vertex which tree it's in, right? Is that component?
Which tree? Yeah, that's the component kind of. This is the component function. The component is the tree. Yeah. So all of these properties are kind of efficiently checkable. Yeah, there's another question.
Sorry, there's one thing I don't understand. So you construct spanning trees, right?
Yes.
And you check them, and you say checking them is of course linear and the edges, I suppose, right?
I guess it depends on the property, but some are linear in the number of edges, some are linear in the number of vertices.
But why don't you just verify Prim's algorithm or something that already computes these? Because Prim compute the spanning trees in linear time as well.
So I think that would be another option of doing it, but it might be, so we did think about that at first, but it might be more complicated to prove one of these algorithms correct. So there is kind of like some invariance that you need to check that the algorithm is doing it correctly, and then you do have to think about, is this efficient in running it in Lean or something.
Okay, so
and this is just an alternative way of checking the connected components.
Yeah, I'm trying to understand the rationale because Prim, for example, like Prim's and other spanning trees algorithms have been verified.
Sure. We could have gone that route. This was we can do a whole bunch of, because for connected components this is going to work, but for some other invariants which are maybe more complicated, it might be way more difficult to prove an algorithm correct. And this is kind of the pattern of how we were doing things. We find some certificate that's easily checkable within Lean that we can compute outside of Lean with some more specialized tools, which are efficiently implemented but maybe not verified. But then we don't need to verify that complicated algorithm. Right. So this is the certificate, and now we want to import it into Lean. And we want basically Lean to check all these properties for us. We don't want to construct the proofs of these properties by hand. These are all just Boolean values. Where we want to go is, we want to tell Lean, this is the data that we computed, and just check all of these. Just run the values and see that all of these are true. So the way we do this, right? Oh yes. And the important thing is that from a certificate like this, from one of these connected component certificates, we can get the connected components of a graph, right? So this is a thing that you have to prove. Right, and to load the certificate, you basically take the graph from Hausdorff, and build some scaffolding in another programming language where we download it there, and we find the connected components, and we create like a JSON file which has all this data. So we load kind of this data into a JSON, and we can read this directly in Lean, and then we can build a function in Lean which basically takes this kind of data that we computed outside and creates an expression in Lean which represents the connected component certificate. And then when we run kind of the lean type checker, it's going to see, okay, I need to check all of these properties, but they're all kind of Boolean values, and then by Boolean reflection, we say, okay, they all have to be true, and then it checks them there and constructs an expression of the type of these certificates. And then we can use the other function to get the actual connected components. Right, so this was the connected components of a graph. And for this one, there is this kind of nice certificate with the spanning trees. We can always compute it. It's easy to compute. Yes, Patrick?
At least, why do you need to do that at the meta level using QQ and not?
Right. So the question is then, once you have this data, how do you go into Lean? Say, okay, this is the Peterson graph. You know, show me that it's connected. One way would be to kind of generate some Lean code. This is the data in Lean, and then just run the Lean whatever's command on that file. It checks it and everything. And we did that at first, but it turned out there's a lot of overhead when Lean checks a Lean file. It does all kind of linting things and everything, and it was kind of more efficient to just directly take the JSON file and then tell the Lean kernel we want to bypass all of that niceness checking. Here is just a Lean expression, just type check this expression. So the meta programming is kind of to bypass having to kind of build nice Lean code. We just want this Lean expression to have this type.
Without using the front end?
Yes, without using any of the front end. This was Mario's help.
Okay.
Because at first when we did this, basically it turned out just loading all the graphs in Lean was very, very slow, because what we did at first is we just generated a whole bunch of Lean code, like Lean files, and say, okay, load this file, import it into another file. And it worked very, very slow, like unexpectedly slow. So then, I don't know, somebody did some benchmarking on this process, and it turned out like 60% of the time was just spent on linting the files. So this was a way of bypassing all of that. You just, put the Lean expression directly into the kernel, and it runs much, much, much faster.
The linter has since been improved.
Right. So this was one. So this was one example where we could compute the certificate nicely, but then there's other examples like the Hamiltonian paths, which is a known NP-hard problem. So if a graph has a Hamiltonian path, there is a really nice certificate. You just have the path. You tell Lean, here's the path, check its path, and it's happy. And check that, it passes through all the vertices, and that's okay. The problem is, what if the graph doesn't have a Hamiltonian path? How do you convince it that it doesn't exist? Because in principle, what you have to say is, I check all the possible paths and check that none of them is Hamiltonian, and that's your certificate. So one way of doing it that we did is encode the Hamiltonian path problem into SAT. So you take the concrete graph that you have and you make basically a propositional formula which represents the Hamiltonian path problem. And then, let's see the next one is. Yeah, so this is kind of what we did. We took the graph into Lean, and then we build a propositional formula of the Hamiltonian path problem of this graph. Then we take this formula and we send it to a SAT solver, and the SAT solver says either yes, right, in which case, so the formula is satisfiable, in which case we can just take the solution to the formula and reconstruct the Hamiltonian path from it, and it's easy then to check that this is indeed a Hamiltonian path. So this is kind of the easy path. The other possibility is that the SAT solver says, okay, this formula is unsatisfiable, but then the SAT solvers these days are able to provide resolution proofs that this formula is indeed unsatisfiable. So then what we can do is we show that kind of the encoding of the SAT, of the Hamiltonian problem into SAT in Lean is correct. So basically, we just need kind of this direction, which says that if the formula F would be unsatisfiable, then there doesn't exist any Hamiltonian path in the graph G. So once we have this kind of theorem, we can now just, if we were able to convince Lean that this proof of unsat of this formula indeed kind of is correct, then we would have the non-existence of the Hamiltonian path. the problem is at the what we're doing is there was no kind of verified SAT-proof checker in Lean. There was one, but kind of it didn't really work. It didn't work well enough or fast enough on these kind of SAT problems of Hamiltonian paths, because kind of it's implemented in the kernel of Lean, and it doesn't handle the kind of formulas big enough for this, because it kind of implements the propositional formula as propositional variables, I think, in Lean, and there's just kind of too many of them, and the formula isn't able to, I don't know, be checked in the kernel of Lean. So, kind of to solve that, what we used is we used an external kind of proof checker, which was verified in some other system other than Lean. And we basically had to say, okay, we're going to trust this proof checker. So within Lean, we say, okay, we trust the results of whatever this proof checker says for this unsatisfiability kind of proof of this formula, right? And then if the proof checker says, okay, indeed, this proof shows that this formula is unsatisfiable, we kind of add an axiom, okay, for this particular formula in Lean, we did believe that it's unsatisfiable. And then from the combination of this axiom and this theorem, we can then show that there isn't any Hamiltonian paths for this graph. So this is how we built it. I have any more slides. Okay, now, okay, so this is kind of the pipeline of checking the other's question.
So the use case of that is that you need some graph from the database to use some theorem to prove some theorem in Lean.
Yeah.
And you want to prove some property. You want to show that that is connected.
Yeah.
Yeah. So you would just assume that it's like you would manually check if the proof checker checks it and says the proof is unset, and then based on that manual check of the certificate checker, you would just add this axiom to Lean.
Right. So in fact, this was kind of a little bit of glue code here. So basically, from within Lean, from within kind of the meta code of Lean, we do some I/O and call the external proof checker, and then see what the proof checker says programmatically. And then if it says yes, and this is correct proof, then we kind of, you know, with meta code, we add this axiom to Lean. We don't put it in manually, but for the given graph, like this is a function or something within Lean.
This is trusted, like not. This is trusted.
So the trusted parts are kind of like the black boxes. I don't know if I should say black boxes, but the thing in the solid line. So we kind of trust Lean, let's say, and we trust the proof checker, and we don't trust the SAT solver. But I guess there's a bit of untrusted code here.
That's what I meant.
Yes.
So this glue code could have a bug, and then you could add this axiom incorrectly.
That's true. So this is a question of how to do better, and I guess.
No, I'm just asking.
No, but it is a very valid point that there could be errors in this glue code. So we could read the output of this proof checker wrong. We could give it the wrong formula or something, and we wouldn't know. So this is a potential problem for introducing errors. Yeah. Okay, yeah, so this is kind of how this works. And I think Katja already mentioned, but we kind of put all of this together into a little library, which is able to interact with the Hausdorff graphs database. You're able to kind of download graphs from within Lean. It does all the loading and the checking of the properties, and then you can kind of use them within, let's say, proofs of existence of graphs. And maybe, how much time do I have? I can do like a little demo.
5 minutes for the questions, if I'm right, but we don't have the chair. Who wants to step in as a chair for the last 5 minutes? Michael's.
You've got 5 minutes, but it's up to you.
I'm going to show this really quickly. We built this little library where you can kind of load these graphs and then check some of their properties. And in this JSON file is kind of the graph and the certificates for the invariants that I talked about. And then to compute these values, it just does the thing that I described. One thing we also build is like a little widget for showing the graph. So if you load the graph, you can kind of display it here. I don't know, move it around and stuff. You can also interact with the Okay, well this is live demos. We can also interact with the HoG database there's a download command. You can give a name of the variable that you want to save the graph in and kind of the HoG ID of the graph. We can execute Python. But basically, if everything worked, this would then download the graph into this variable and we could kind of display it here. And just imagine this works.
The curse of the demo. I know what's wrong, it's just...
Then we also have like a little kind of DSL where we have like a search command where we can put in a bunch of the invariants. And again, if this worked, it would kind of search the Hausdorff graphs database and it would give like a little list of the graphs here in the info view, and you could kind of load them into Lean. And then I guess another thing is we build like a little tactic where if you have kind of goals of this kind, where it's kind of like an existence of a graph. So we say, there exists a graph which is traceable and its vertex size is greater than 3, and something about minimum degree and vertex size. And this tactic, which basically says find example, and again it goes into the Hausdorff graphs database. It sees if there's a graph that satisfying these properties, and it loads it and tries to use it to close this kind of goal with checking the invariants. Yeah, that's kind of what we have. And yeah, I think that's it. Yeah, thank you.